Hello class, so today here in Statics of Rigid Bodies, we are now down to our seventh lesson, which is about Introduction to Equilibrium. So for this topic, our intended learning outcomes are as follow. So the first one is students must be able to recite the concept of equilibrium, and the second one is students must be able to illustrate free body diagrams. So let's start our discussion. So for equilibrium of force systems, we use the term equilibrium to designate the condition where the resultant of a system of forces is zero. So from our previous discussions, we have discussed about how to solve the resultant of different force systems, right? So here in this topic, okay, the resultant of all the force systems that we are going to talk about will be zero. Okay, since all the systems that we're going to talk about here in this topic are in equilibrium. Okay, so if the resultant is zero, therefore, the horizontal component of that resultant will also be zero. Okay, so that's why we're going to use here this equation wherein the summation of all the horizontal forces in the system is equal to zero. And also, if the resultant is zero, therefore, its vertical component, okay, will also be zero. Okay, and the vertical component, that is equivalent to the summation of all the vertical components of the forces in the system. And that is EFD, and that will be equal also to zero. Okay, and also, if our resultant is zero, okay, therefore, the moment, okay, of the system, okay, is also zero, will also be zero. So we have discussed also from our previous topics that we have a special case wherein the resultant is zero, but there is a couple. But here in this topic, okay, so the resultant will be zero, and at the same time, the resulting moment will also be zero. So these three equations, we are going to use them. Okay, all throughout this discussions about equilibrium of force systems, that the summation of all the horizontal forces in the system will be equal to zero. The summation of all the vertical forces in the system, or vertical components of forces in the system, will also be zero. And the summation of moment, okay, in all the systems that we're going to discuss, will always be equal to zero. Okay, so let's proceed. So for equilibrium of force systems, it is important that we learn first, okay, the concept about free body diagram. So what is free body diagram? So free body diagram, it is an isolated view of a body which shows only the external forces exerted on the body. So the free body, it may consist of an entire assembled structure or any combination or part of it. Okay, so we can construct, okay, the free body diagram, let's say, of an entire structure. But we can also construct the free body diagram of each body, okay, that is part, okay, of the structure. Okay, so it is important that we have knowledge, okay, in constructing free body diagram of the entire structure, okay, and the free body diagram of every part, okay, or every body, okay, that is part of the structure, okay, because it will be impossible, okay, to solve systems of forces in equilibrium without having knowledge nga, no, in constructing free body diagram. So this is very, very important. Okay, so forces that act on a body can be divided into two general categories. There are reactive forces, okay, or simply reactions, and the second one is applied forces. Okay, so reactions or reactive forces, they are forces that are exerted on a body by the supports. Okay, so the forces, okay, that are produced by the supports are called reactions, okay, to which it is attached. So forces acting on a body that are not provided by the supports, okay, they are called applied forces. Of course, all forces, both reactive and applied, must be shown on free body diagrams. Okay, so these are the two forces that must be reflected on your free body diagram. So these are the external forces that is being mentioned, okay, that are being mentioned in the definition of free body diagram. So we have to show, okay, the external forces exerted on the body, and those external forces are reaction forces or reactions, or these are the forces nga that are provided by the support, and the applied forces. Okay, so for applied forces, the self weight, okay, of the body, okay, is actually included, okay, in that type of force, no, in applied forces. Okay, so those two forces, they must both be reflected and shown, okay, on your free body diagram. Okay, whether it is a free body diagram of the entire structure or free body diagram of a part, okay, or a body that is part of the structure. Okay, so let's consider this structure. So as you can see here, we have here a structure. Okay, we have here a cylinder B, no, and it is supported by this rod AB. Okay, and this member CD. Okay, so from this structure, we can actually construct, okay, a force system. So how? Okay, so we can construct here a force system, okay, by constructing its free body diagram. Okay, so for this structure, we can actually construct the free body diagram of this entire structure. Okay, so this will be the free body diagram of that entire structure. So it reflects here, okay, the forces that are involved here. So the forces that are involved here again are reactive forces and applied forces. Okay, so also we can also construct a force system, okay, by constructing the free body diagram of each part, okay, of this structure, no. So let's say we have here the rod AB. Okay, so from that rod AB, we can construct its free body diagram. Let's say it will be its free body diagram. Okay, so this forms a force system, right? And also for this cylinder, we can also construct its free body diagram. So let's say this will be the free body diagram. So there will be forces here that are shown and reflected, right? So also for this member CD, we can also construct its free body diagram. So for this structure, again, we can construct its free body diagram, okay, as a whole, no, as an entire structure. And at the same time, we can also construct its free body diagram or the free body diagram of every part, okay, of the structure. Okay. So these are the steps in constructing free body diagrams. So the first one, a sketch of the body is drawn assuming that all supports such as surfaces of contact, supporting cables, etc. have been removed. Okay, so all the different types of supports, I will discuss that, okay, in our succeeding slides. Okay, so the second step, all applied forces are drawn and labeled on the sketch. The weight of the body is considered to be an applied force acting at the center of gravity. So again, applied forces, these are the forces that are not provided by the support. So they are external forces that are applied on the body. Okay, so the weight of the body, okay, it is considered to be an applied force. So, okay, and it always acts, okay, at the center of gravity, okay, of that body. Okay, so let's say your body is in a geometric shape of, let's say, a circle. Okay, so the weight, okay, the weight of that body, okay, it will be applied, okay, or it will act, okay, at its center. So the center, okay, of the circle is at the center of the circle. So the weight, okay, of that body, it will be applied there, no, at that center. Now also any shape, okay, any shape of a body, okay, so your weight, okay, your weight or the weight of that body, okay, it will always act, okay, or applied, okay, at its center. Okay, so that's where you apply, okay, the weight, no, as an applied force, okay, on a body. Okay, so the third step, the support reactions are drawn and labeled on the sketch. If the sense or direction is unknown, of a reaction is unknown, it should be assumed. Okay, so the solution will determine the correct sense or direction. A positive result indicates that the assumed sense or direction is correct, whereas a negative result means that the correct sense or direction is opposite to the assumed sense. Okay, so the support reactions, again, they are the reactions that are provided by the support. So we are going to discuss, okay, the reactions, okay, that are provided by different supports. Okay, we will discuss that in our succeeding slides. Okay, so the direction, okay, of application, okay, of the reaction forces are actually assumed. Okay, so um, our assumption, no, it can be correct, no, depending on our analysis of the structure. Okay, so also our assumption, it can be determined if it is wrong or right, okay, or right assumption, okay, depending on the solution. Okay, so if in your solution, okay, it turned out that, let's say you assume a direction, okay, but in your solution it turned out that your assumption is negative, or the resulting answer in your solution is negative. Okay, so that means that your assumption of the direction is wrong. Okay, because the answer is negative. Okay, so from that, you can correct your assumption. Okay, so it's okay that you assumed it wrong because it was determined naman, no, in your solution. Okay, so from that, you can correct your assumption. Okay. So for the last step, so all relevant angles and dimensions are shown on the sketch. So it will be easier, okay, if in our constructed free body diagram, okay, we show, okay, all the angles or all the dimensions, okay, so that we will not get confused, okay, in our computation. So it is important step also. Okay, so now let's talk about support reactions. So when you have completed the procedures, okay, discussed in the previous slide, okay, you will have a drawing, okay, and that drawing will be your free body diagram. Okay, it contains all of the information necessary for writing the equilibrium equations for the body. Okay, so the most difficult step to master in the construction of FBDs is the determination of the support reaction. So the following discussion shows the reactions exerted by various supports. It also lists the number of unknowns that are introduced on an FBD by the removal of each support. To be successful at drawing FBDs, you must be completely familiar with support reaction. So we will start now our discussions about different support, no, and the reaction forces that they provide. Okay, so let's start our discussion. Okay, so it is also helpful to understand the physical reasoning that determines the reactions at each support, which are described below. So the first support that we're going to talk about are flexible cables. Okay, so flexible cable of negligible weight. Okay, so here we assume, okay, all flexible cables as weightless, no. So if we are going to consider its weight, no, it will be another topic, no, and we're not going to discuss that here in statics. Oh, so that will be another topic, no. So again, all flexible cables here, we will assume them as weightless, no. We will neglect, okay, their weight, no. So a flexible cable exerts a pull, okay, or tensile force, no, in the direction of the cable. So with the weight of the cable neglected, the cable forms a straight line. If its direction is known, removal of the cable introduces one unknown in a free body diagram. So the magnitude of the force exerted by the cable. Okay, so let's say we have here this body, no, and it is supported by this cable. Okay, so if we are going to construct the free body diagram, okay, of this body, okay, with this support, okay, so again, okay, this support, okay, it will provide a tension force. So it is always pull, no, it cannot be a compression force, no. So cable, its reaction, okay, is always pull. Okay, so it will pull, okay, this body. Okay, it will pull this body, and the direction, okay, of that reaction force, which is a tension force, it will always be along the direction of the cable. So if the cable is directed, let's say, theta from the horizontal, so the reaction force T, okay, this reaction force T should also be theta from the horizontal. Okay, so that will be the application, okay, or the direction of application of the reaction force that is provided by this cable. So it will always be this way. No, it is always pull. Okay, it can never be a compression force, no? So because it is a cable, okay, of course it will pull, okay, the body. Okay, and from that, no, it will introduce a one unknown, okay, in your free body diagram. Okay, so this will be the one unknown, this tension force. No? If the direction, if this theta, okay, if this inclination, okay, is given. Okay, so there will only be one unknown, okay, for this type of support, no, the reaction force that it provides. So the second support that we're going to talk about is frictionless surface. So for this support, no, we will assume that the surface has no friction. Okay, because if you are going to consider friction, it will actually introduce a reaction, another reaction force. No, so here in this type of support, we will assume it as frictionless. No, the surface is frictionless or smooth. No, so also the body here will have a single point of contact, okay, on the surface. Okay, so when a body is in contact with a frictionless surface at only one point, the reaction is a force that is perpendicular to the surface acting at the point of contact. This reaction is often referred to simply as the normal force. So therefore, removing such a surface introduces one unknown in a free body diagram. So the magnitude of the normal force. Okay, so let's say we have here a body. Okay, so let's say this body. Okay, let's say we have here this surface, no, and if we are going to put this body, okay, on this surface, okay, so this is lying now, no, on the surface or nakapatong. Okay, so as you can see, this is stable, okay, because this surface is actually providing a support, okay, for this body, okay, and the support that it provides, okay, actually provides a reaction force. Okay, and that reaction force, if we are going to construct the free body diagram of this body, so the reaction force that acts, okay, on this body provided by the surface will be this force, no? So this force is a normal force. Okay, so this normal force, okay, this is applied, okay, at the point of contact of this body, okay, to the surface. It will be applied at the point of contact, and also it will be applied, okay, perpendicular to the surface. So if this is the surface, okay, so uh, that normal force should be perpendicular or 90 degrees, okay, from that surface, no? So that will be the application, okay, of that normal force to this body, no? So that reaction force is actually called normal force, no? So let's say we have here this surface. So this is a frictionless surface. Okay, so let's say this is the body, okay, and this body is leaning or nakapatong, okay, to this surface. So this surface will provide a reaction force on this body, okay, and the application, okay, of that reaction force, which is the normal force, no, that the application of that, okay, will be at the point of contact of this surface, okay, and this body. So the point of contact of this two of this surface and this body will be at this point, right? Okay, so that will be the point of application, okay, of your normal force. And also, your normal force should be applied, okay, perpendicular. Okay, perpendicular to the surface. So this is the surface. So since this is inclined, so the perpendicular, the normal force will be applied here 90 degrees, okay, from the incline, right? So it will be applied this way. Okay, again, it will be applied perpendicular to the surface, and it will be applied at the point of contact of the surface and the body. Now, let's say our body is a box, no? Let's say or a block, no? So let's say this box or block is leaning on this surface. Okay, so as you can see, as we have said earlier, that the point of application of the reaction force should be at the point of contact of the surface and the body. But in this case, the contact here of the body and the surface is not just a point. Okay, it's actually this, right? The point of application is this line, right? So, uh, here the force here, the reaction forces will actually be, or the normal force will actually be a pressure, no, it's not a force, it will not be a force, so it will be like a rectangular force. Okay, but as we know, as we have discussed in parallel force systems, no, that we can actually solve for the equivalent point load of that rectangular load, right? So it's the same here. Okay, that if the reaction force here is a rectangular force, we can compute its equivalent point force, which will be this normal force. And its point of application will be at the center, okay, of the point of contact, okay, of this body, okay, to the surface, which is at this point. So this will be applied at that point, no, and it will be applied 90 degrees from the incline, no, so it will be perpendicular to the incline surface. Okay, so this will be the reaction force that will be provided, okay, by this smooth surface or frictionless surface. So this will just be one unknown, okay, if the support is just a frictionless surface. So only one reaction force, unknown reaction force for this support. Okay, so the third support that we're going to talk about is a roller support. So a roller support, it is equivalent to a frictionless surface. It can only exert a force that is perpendicular to the supporting surface. The magnitude of the force is thus the only unknown introduced in a free body diagram when the support is removed. So let's say we have here this body and it is actually supported by this roller. So rollers are drawn this way. Okay, so like this or like this, no? So, the reaction force that will be provided by that roller, okay, will just be equivalent, okay, to the reaction force that will be provided by the surface. Okay, so since that roller is just actually lying, okay, or leaning on the surface, okay, so it will also it will just also provide a normal force, and the point of application will be at the point of contact of the roller and the surface, okay, and it will be perpendicular, okay, to the surface. Okay, so this will just be the unknown reaction force, okay, that will be provided by a roller support. Okay, so this is just a single unknown reaction force. Okay, so these are real life examples of roller supports. Okay, so this shoes, okay, it is supported by these rollers, okay, and the support that it provides is a normal force. So that normal force will be perpendicular to the surface where this roller is lying. Okay, so same with these rollers and this roller. No, so these are examples of rollers in roller support, okay, in real life. Okay. Okay, so the fourth support that we're going to talk about is surface with friction. So here, okay, we will consider, okay, the effect of friction, okay, and because of friction, it will introduce, okay, a reaction force called friction force. Okay, so a friction surface can exert a force that acts at an angle to the surface, no? So the unknowns may be taken to be the magnitude and direction of the force. However, it is usually advantageous to represent the unknowns as N and F, the components that are perpendicular and parallel to the surface respectively. So the component N is called the normal force and F is known as the friction force. So let's say we have here a surface, okay, and this surface has a friction, okay, so we will consider the friction, and if there is a body, okay, lying on this surface, so the support, this support, okay, or this surface, okay, it will produce, okay, or provide, okay, a reaction force. So the first reaction force will be this normal force, okay, it is the same, no, it's the same normal force as the surface without friction, no. So it will be that same normal force, so it will be applied at the point of contact and perpendicular to the incline, and also there will be a friction force, okay, and this friction force will be applied, okay, parallel to the surface. Okay, so it will be parallel to the surface. Okay, so this two reaction forces, okay, it will be provided by surface with friction. So there will be two unknowns here, okay, if we construct the free body diagram of a body, okay, wherein the support is a surface with friction. So there will be two unknown reaction forces, that is friction force and normal force. Okay. So there will actually be a separate discussion, okay, for analysis, no, analysis of force systems, okay, wherein the support has friction. Okay, so there will be a separate topic for that. Okay, so the fifth support is pin support, or simply called hinge. So a pin, it is a cylinder that is slightly smaller than the hole into which it is inserted, as shown in A. Okay, so this is A. So let's say we have here a body. Okay, so it has a hole here. Okay, and inside that hole, okay, there is an inserted pin. Okay, so that pin, okay, that pin serves as the support, okay, for this body. Okay, so that pin, okay, neglecting friction, it can only exert a force that is normal to the contact surface. So where will be the contact surface of the pin and the body? So it will be somewhere here, right, at this point, no? So that will be the point of contact of again, of the body and the pin, no? So at that point of contact, okay, so the normal force, okay, there, that will be the point of application of this, let's say, this normal force R. Okay, so the thing here is that there will be an introduced two unknowns. Okay, this normal force R, okay, and this alpha. Okay, so the magnitude of R and the angle alpha that specifies the direction of R is unknown, because the point where the pin contacts the surface of the hole is not known. So more commonly, the two unknowns are chosen to be perpendicular components of R, such as Rx and Ry, as shown in C. So this is C, no? So instead of using R and alpha, okay, as the unknown quantities, okay, for the reaction force that is provided by the pin, okay, we will instead use, okay, two reaction forces, okay, which will be equivalent to these two unknown, no? So that will be the horizontal reaction and vertical reaction. So for pins, no, so we will always use, okay, we will always use two unknowns, okay, that instead of using R and alpha, we will instead use horizontal and vertical reaction. Okay, so they are the reaction forces that are provided, okay, by pin support or hinge, no? So again, there will be two reaction forces here, one horizontal, okay, and one vertical. Okay, one vertical reaction force. So again, there are two unknowns, okay, unknown reaction force, okay, that is provided by pin supports or hinge supports. Okay, so it's always horizontal and vertical reaction. Okay, so these are examples of pin or hinge support in real life, no? So as you can see here, this is the body and there is a pin here. Okay, so this is a pin, no? Pin support. So, or this body is pin connected, no? So same here. So it is pin, no? This body is pin, okay, here. And also for this body, no? So it is pin here, no? So these are examples of pin supports or hinge supports in real life. Okay, so there are two reaction forces, okay, that this pin supports provides. Okay, so they are horizontal and vertical reactions. No, yun. Okay. So the last support that we're going to talk about is built-in or cantilever support, or also called fixed support. So a built-in support, also known as a cantilever support, prevents all motion of the body at the support. Translation, horizontal or vertical movement is prevented by a force, and a couple prohibits rotation. Therefore, a built-in support introduces three unknowns in a free body diagram: the magnitude and direction of the reactive force R. These unknowns are commonly chosen to be components of R, such as Rx and Ry, and the magnitude C of the reactive couple. So for fixed support or built-in or cantilever support, there are actually three reactions. So these three reactions are horizontal reaction, vertical reaction, and a moment reaction or a couple reaction. Okay, so it's important that you understand this concept, no? So for built-in support, no? So for built-in support or fixed support, okay, so since it is fixed, so let's say this is the body, no? So since let's say this is the body, so it is supported here, and its support is fixed, no? So ibig sabihin, meaning to say, okay, it is restricted. Okay, it is restricted to move to the left or to the right. It is also restricted to move downward or upward. No, it is also restricted to rotate. Okay, since it is fixed here. Okay, at this point, it is fixed here. No, so those restrictions actually, okay, will determine the reaction. Okay, so if it is restricted, meaning to say it will react. Okay, that support will react. Okay, or that body will react. Okay, so let's say this body, no, it is restricted to move horizontally, right? Since it is fixed here. Okay, so that's why it will have a reaction or horizontal reaction. Okay, if it's restricted to move uh, to the right or to the left or horizontally, no, therefore it will have a horizontal reaction. Also, if it is restricted to move vertically, therefore it will have a vertical reaction. Okay, and also if it is restricted to rotate, okay, if it is restricted to rotate, okay, therefore it will have a moment reaction. Okay, so that's the explanation, okay, for these reactions, no? Why there are three unknown reactions here. It depends on the restriction. It's also the same actually for let's say for roller support. So your for roller support, there is only one there's only one reaction force, right? It is the normal force or the vertical force. Let's say the surface is a horizontal surface, no, and you have your roller. Okay, you have your roller. So the reaction force is just a normal force, which is which is a vertical force, right? That is a vertical force because that roller is only restricted. Okay, that roller is only restricted to move upward or downward. Vertically, it is restricted to move vertically. Okay? So since it is restricted, it will have a vertical force or a vertical reaction. Okay? And the roller, as you know, it has the freedom. Okay? It has the freedom to roll horizontally, right? So it is not restricted to move horizontally. That's why there is no horizontal reaction force. Okay? And also, it has the freedom to rotate. So if it has the freedom to rotate, there will also be no moment reaction. Okay? There will be no moment reaction. Right? Now, for hinge support, as you know, a hinge support, there will be two reactions, right? One horizontal and one vertical forces because a hinge or pin connection or pin support, okay, the body, if it is supported by pin support or a hinge support, that body has the freedom or restricted rather. That body is restricted to move. Okay, let's say this is this is the, let's say this is the body. Okay, and it is pin connected somewhere here. It is pin connected. There is a hole here. Let's say there is a hole here and there is a pin inserted here. So it is supported by a pin, no? So this body, no, it has no freedom, okay, or it is restricted. It is restricted to move to the left or to the right because it is pinned. Okay, that's why it has a horizontal reaction. And also, it is restricted, okay, to move upward or downward. Okay, so that's why it has a vertical reaction. Okay, but okay, this pin actually has the freedom to rotate. It is not restricted to rotate. That's why there will be no moment reaction. Since it is pin, so for pin, right, it will be rotated. It can be rotated, right? So there will be no reaction for moment, for rotation. Okay, that's why. Okay, so it's important that we understood stand it that way, no? Uh, that's why the reactions are like that. Okay, so these are examples of fixed supports in real life, or cantilever support or built-in support, no? So this beam, no, is actually fixed supported here, no? So it has no freedom to move to the right or to the left, or it has no freedom also to move vertically, and it has no freedom to rotate. Okay, that's why there will be three reactions: horizontal reaction, vertical reaction, and a moment reaction, no? So also this is an example also, no? Okay, of fixed support. So for the summary of the different types of support and the reaction forces that they provide. Okay, so again, if your support is a cable, so there will only be one unknown reaction force, and that will be a tension force. So this is a pull, no? So its direction will always be a pull. Okay, and its application will just be along the direction of the cable. Okay, so the second support is frictionless surface, no? So for this support, no, there will only be one reaction force, which is a normal force, and it will be applied at the point of contact and perpendicular to the surface. Okay, now for surface with friction naman, so there will just be an added friction force here. Okay, so for roller support, again, it's also equivalent to frictionless surface. Okay, so there will only be one reaction force here, which is a normal force, and the point of application of this is at the point of contact of the roller and the surface, and it is perpendicular, okay, to the surface. And now for pin support naman, no, so there are two reaction forces, okay, that it provides, one horizontal reaction and one vertical reaction. And for the last support, it is fixed support. So there will be three reactions here: one horizontal reaction, one vertical reaction, and one moment reaction. Okay, so these are the unknowns, the number of unknowns, okay, or unknown reaction that this supports provide. Okay, so since we have already learned about support reactions, we can now start to construct free body diagrams of structures, no? So let's try to solve this sample problem number 1. So a 200 Newton cylinder is supported by a horizontal rod AB, assumed to be weightless, and rests against the uniform bar CD, which weighs 100 Newton. Draw the free body diagram of rod AB, of the cylinder, of bar CD, FBD, and FBD of the entire structure. So assume the pins at A, B, C, and D, and rollers to be smooth and frictionless. Okay, so we are going to construct the free body diagram of the parts of this structure, and the free body diagram of the entire structure. So we are going to follow, okay, the procedures or the steps, okay, in constructing free body diagram. So let's start. Okay, so for this problem, we are asked here to construct the free body diagram of A rod AB, letter B, the F body of the cylinder, letter C, the FBD of bar CD, and letter D, the FBD of the entire structure. So let us first construct the free body diagram, okay, of rod AB. So rod AB is this, no? It is here. Okay, so we will follow our procedure in constructing the free body diagram. So our first step is we have to draw, okay, the body, okay, assuming that all the supports, okay, are removed. Okay, so for rod AB, so it is actually supported by a pin support here at A, okay, and it is also pin supported here at point B. So we will remove them, no? Okay, so after removing that, no, so we will now draw the applied forces and label them on the sketch. So in this case, the applied force here will be the weight, okay, of the rod. Okay, but since in the problem it was mentioned that the weight of the the rod, or the rod AB is weightless, no, so the weight will be 0. Okay, so just in case that if there's a weight, no, for a body, no, so let's say we have a weight for this rod AB, so it will be applied at the center of gravity of this rod AB, no, so it will be at the center of rod AB. So let's say this will be, here will be the center, okay, of rod AB. So this is the point, okay, where we will apply, okay, the weight, okay, but here this is actually equal to 0. Now after that, we are going to draw now the reactions, okay, that are provided by the support. So here, at A, our support here is a hinge or a pin, no? And also dito sa B, here at B, the support here is also a pin, okay? So for A, no, since it is pin connected, there will be two reaction forces here. So that will be a horizontal reaction and a vertical reaction. So we will label this as AH and the vertical reaction as AV. Okay, so also at B, at point B, so this is also a pin. So there will also be two reaction forces here. So this will be horizontal and vertical reaction. So we will label them as BH and BV. Now, we just actually assume, okay, the direction of these reaction forces. Okay, but here, since we know that this weight, okay, it is actually downward, right? So it is all your the weight, okay, the weight of the body, okay, it's actually always directed downward since it is weight, right? So since the weight is directed downward, your AV, okay, since it should support, no, since it should support this weight, no, the weight of this rod AB, it should be directed upward, your AV and BV. But the thing here is that since your weight here is 0, okay, so there will be no weight that this AV and BV will support. Okay, so meaning to say, if we sum up vertical forces, if your W is 0, if your weight is 0, your AV and BV will just be 0. So redrawing this free body diagram, so we can remove AV and BV since we know that they will just be 0 since our weight here is 0. So only AH and BH will be reflected here or shown here in the free body diagram of rod AB. So this will now be the free body diagram of rod AB. Now, for the second one, okay, so actually for our fourth step, no, for constructing free body diagram, we have to show all relevant angles and dimensions, right? So that's the fourth step. But since there is no actually dimension here for rod AB, no, so we will skip that step, no. So now we will now proceed to constructing the free body diagram of the cylinder. So the cylinder is here. Okay, so again, our first step, we have to draw the body or the cylinder, okay, wherein we assume that the supports are removed. So let's say we draw this cylinder, no. So after that, we have to draw the applied forces. So the applied force here will be the weight, okay, of the cylinder. Okay, so in the problem, it was given that the weight of this cylinder is 200 Newton. Okay, so this will be the weight. So that weight will be applied at the center of gravity of this cylinder, no? So it will be at the center of this circle. So it will be applied at that point. Okay, so that will be W is equal to 200 Newton. Okay, so after that, no, we are going now to apply, okay, the support reactions, okay, or the reaction forces that are provided by the support. So in this case, the supports, okay, of this cylinder. So what are the supports that supports, no, this cylinder? So it is supported by this pin here at point B, and also this cylinder is leaning at at bar CD, no. So this bar CD will serve as a support also for this cylinder CD. So since it is leaning at bar CD, so your CD, no, the support that it provides will just be equivalent to frictionless surface, no? Ayun. So, uh, for um, for the support at point B, so it has been connected here. Okay, so actually, we have already drawn the reaction forces at point B, right? So we have already drawn that here in the FBD of rod AB. Now, we have a rule here, okay, that this same reaction force BH, okay, so since we already know that BV will just be 0, so if we transfer this BH, okay, to another body, let's say from rod AB, we transfer this BH to the FBD of the cylinder, okay, so it will be directed opposite. No, it will be oppositely directed. Okay, again, if you transfer a reaction force from one body or from the FBD of one body to the FBD of another body, it should be oppositely directed. So if your BH is directed to the left here at this free in the free body diagram of rod AB, when we transfer it to the FBD of the cylinder, it should be directed to the right, no? So it should be oppositely directed. That's why your BH here will be directed, okay, to the right, no? So uh, that's our rule, no, for transferring a reaction force from one body to another, no? So it should be oppositely directed. Now, since this bar CD, no, it will serve as a frictionless surface, okay, that will support this cylinder. So the only reaction force that it will provide will be normal force. So that normal force, it will be applied, okay, at the point of contact of the cylinder and the bar CD. So the point of contact is somewhere here. Okay, and also the application of this normal force, it should be perpendicular to the inclined surface, to this inclined bar CD. Okay, so it will be 90 degrees. Okay, it will be perpendicular. Okay, so this normal force, okay, if we extend actually its line of action, um, it will actually cross or pass through, no, the center of the circle, no. So all these forces, no, this BHW and this normal force, they will all meet, okay, at the center of this cylinder, no. So this will actually form a concurrent force system, right? Ayun. So this will now be the free body diagram of the cylinder. And also, for our fourth step pala, no, so we need to show here, okay, the relevant angles and dimensions. So here, as we know that the angle of the incline, okay, of bar CD is 30 degrees, no, from the horizontal nga, no. So if this is perpendicular to the incline, if we draw here a vertical line, no, so the angle of this normal force from that vertical line will just be equivalent to 30 degrees, no, to the angle here from the horizontal. So again, if your angle here from the horizontal of this incline, okay, is 30 degrees from the horizontal, if I draw a vertical line here, okay, and measure the angle of this normal force from the vertical line, it will be 30 degrees as well. Okay, so if we extend this, no, and draw here a vertical line, so this will also be 30 degrees. So this normal force will be 30 degrees from the vertical. Okay, so this will now be the free body diagram of the cylinder. Now, let's proceed to constructing the FBD of bar CD. Okay, so this will now be the free body diagram of bar CD. So again, our bar CD is this bar, no? Okay, so again, our first step, we have to assume, okay, or we have to draw this bar CD, assuming that the supports are removed, no? So in this case, the support of bar CD are a roller at point C, no? So this is a roller. Okay, and here at point D, this is a hinge or a pin support. Okay, so from here, okay, so from that, no, our second step is we have to draw applied force, which is the weight. No, in this case, our applied force is the weight of the rod, and it is mentioned in the problem that the weight of the rod is 100 newton. So that weight will be, of course, it will be applied downward, and it will be applied at the center of gravity of rod CD. So it will be at the center of rod CD, and it will be somewhere here. So that's the point of application of its weight, which is equal to 100 newton. So here, as we know that at this point, no, there's a normal force here, and this normal force or this reaction force, if we transfer it, okay, to the free body diagram of bar CD, so if we transfer it, it should be oppositely directed. So in this case, actually, this normal force will also serve as an applied force, no, for bar CD, since this is not provided by a support, no. So in this case, the point of contact between the cylinder and the bar CD, okay, so it's not support, it's not a support, no. So it will now be a applied force here, okay, if we transfer this normal force, okay, at bar, because here this cylinder, it will be carried, okay, it will be carried by the by this rod CD, no. So it will be considered, no, as a load here, this normal force, no. Ayan. Anyway, so again, for our third step, we have to draw the reaction forces that are provided by the support. So in this case, at point C, our support here is a roller. So the reaction force that will be provided by a roller will just be a normal force also, right? So here, we are the reaction force, we will label it as RC, no. So that will be the reaction at point C. So it will just be a normal force, it will be perpendicular to the surface, okay, wherein the roller, okay, is lying, no. So since it is just horizontal, no, so your normal force for this roller will just be vertical here, no. Ayun. So also for at point D, no, so our support here is a hinge. So again, there will be two reaction forces here, one vertical and one horizontal. So we will label, okay, the horizontal reaction as DH and the vertical reaction as DV. Okay, so from here, for your fourth step, you have to draw here or include here or show here the dimensions and the angle. So we have here 7 feet, no, from point C up to this point, to the point of application of the normal force, and also um, from the application of the normal force to point D, it is 3 feet, no. And also, we have here 30 degrees inclination. So since the normal force, it is perpendicular to the incline of this bar CD. So if we draw a vertical line here, so the angle of this normal force from the vertical line, it will just be also 30 degrees. Okay, so this will now be the free body diagram of bar CD. Okay, so now let's proceed to letter D. So we will now construct the free body diagram of the entire structure. So our rule for constructing the free body diagram of the entire structure. So we just have to show the reaction forces or the reaction forces, right, that are provided by the main supports. So how are we going to know what are the main supports, okay, for this structure? Okay, so we can know the main supports by analyzing this, no. So for example, no, so this cylinder, what supports this cylinder? Okay, so it is actually supported by this pin at B and this bar CD, no. So it is supported by these bodies, by rod AB and by bar CD, no, or pin at B, no. Ayun. So what now supports this pin at B? Okay, so it is actually supported by this hinge at point A. right? Now, what supports this hinge at point A? So there is no other supports that supports the hinge at point A, right? So meaning to say this hinge at point A is a main support. Okay, so meaning to say we will show here, okay, the reaction forces that are provided by hinge at point A, no? And also, uh, this cylinder, it is also supported by bar CD, but now, what supports this bar CD? So this bar CD is actually supported by um, roller support at C and a hinge support here at D, right? So now what supports this the roller here, okay, or the surface here, okay, the frictionless surface here, what supports it? So no other support, no? So meaning to say, this roller at C, okay, this is actually a main support. And also, this hinge at D, this is also a main support. Okay, so we will now show, okay, in the free body diagram of the entire structure, we will show the reaction forces, okay, of the main supports. And also, we are going also to show here the applied forces which are the weight, okay, of the rod, of the cylinder, and the bar CD. Okay, so this will now be the free body diagram of the entire structure of this ano no of this given structure. Okay, so the reaction forces here at A will be AH and AV. Okay, for point C, the support is here is a roller, so there will only be one unknown reaction force, which we labeled as RC. And here at point D, so there will be two reaction forces as well. And here we show here the weight of the cylinder, but as because since we know that the weight of rod AB is zero, so we did not include that here anymore, no? So, and also we know that rod CD has a weight of 100 newton, so we also show that here. So this will now be again the free body diagram of this entire structure. Now, let's proceed to sample problem number 2. So, the cylinder C in the figure below weighs 1,000 pounds. Draw a free body diagram of cylinder C and rod AB. So, we are asked here to solve for the free body diagram of cylinder C. This is our cylinder C and rod AB. So, this will be rod AB. So, let's start. So for this problem, again, we will start to construct the free body diagram of cylinder C. So our cylinder C is this. Okay, so our first step to construct its free body diagram, we have to draw this cylinder, okay, assuming that its supports are removed. So in this case, the supports, okay, of this cylinder C, okay, it is actually supported by this surface, no, by this surface here. So this is a frictionless surface, okay, and it is also supported by this rod AB. So this will just be equivalent, okay, to surface also, right? So it's like a surface also that supports this cylinder. See, so those are the supports. So we will remove them, okay, and after that, okay, after we draw our cylinder, okay, we are going to show also or draw the applied force. So in this case, the applied force is the weight of the cylinder, and the weight of the cylinder is 1,000 pounds. So it will be applied in the center of gravity. So this will be the center of gravity of this circle. Also, it will be applied here. Okay, the weight will be applied here. It will be downward, of course. And after that, we are going now to show, okay, the reaction forces, okay, that are provided by the support. So for the support here, okay, in here, no, so this is a frictionless surface. So the reaction that it will provide will just be a normal force. So the point of application of this normal force will just be at the point of contact of this cylinder and this surface. So it will be here. Okay, and also the application of this normal force will be perpendicular to this inclined surface. So this will be 90 degrees, no, from this incline. Okay, and also if this is 60 degrees here, Okay, so if this is 60 degrees here, so meaning to say this degree, okay, here, the remaining angle here, okay, from the horizontal, it will be 90 minus 60. So that will be 30 degrees. So this will be 30 degrees, this angle from the horizontal. Okay, so the inclination of this surface, okay, from the horizontal is 30 degrees. So if I draw a vertical line here and measure the angle of the normal force from that vertical, it will just also be 30 degrees. Okay, so that will be the angle of that normal force, okay, from the vertical line that we have drawn here. And also, we also have here a support, okay, that this bar AB provides, no? So this will just be an equivalent to surface, no, to the reaction force that a surface or frictional surface is providing. So in this case, it will provide a normal force, no? So we will name this as N sub E, okay? This reaction force. So this will be a normal force, and its point of application will be at the point of contact of this cylinder, okay, and the rod, no? Or tama, rod AB, no? So this will be the point of contact. So here will also be the point of application of our reaction force. And also, this will be perpendicular to our surface. So this is vertical. So your NE will just be horizontal, na applied horizontally. Okay. So also, if we are going to extend the line of action of this NE, okay, and this N, no, normal force here. So they will all meet here at the center. So this will also form a concurrent force system. Okay, so this will now be the free body diagram of cylinder C. Now we will proceed to the free body diagram of rod AB. So for the free body diagram of rod AB, so our rod AB is this. Okay, so this will be the rod AB. So our first step, again, we have to draw bar AB, okay, assuming that the supports are removed. So in this case, the supports here are here, okay, at point B, it is supported by a cable. Okay, so this is a cable. Okay, and here at point A, it is supported by a hinge support. No, so we will remove them. So we will draw bar AB, and after that, we are going to apply the applied force or the weight, no, of bar AB. But in the problem, no, so it's not mentioned that uh, there was no mentioned weight for rod AB. So meaning to say, we will assume or neglect, okay, the weight of rod AB since it's not given. Okay, so we will assume that this rod AB is also weightless, no? So there will be no weight here. Okay, so but here, okay, so the reaction force here at point E, okay, which is a normal force from the FBD of cylinder C, we are going to transfer that, okay, in the bar AB, no? And if we transfer this N sub E, it should be oppositely directed here, but it should be, of course, it should be applied at the same point of application. So here it is applied here, it is applied here. So it should also be applied at that same point, no? But it is oppositely directed. So this ME, this will actually serve as the applied force, okay, for AB, since this reaction force is not actually a support, okay, or a reaction force that is provided by the support. So this is not a support, no, for bar AB, but instead this bar AB is supporting this cylinder, right? So this cylinder which will actually push, okay, this bar AB, right? Okay, so that will be the applied force, okay, for this bar AB or rod AB. Now, for the support of rod AB here at point B. So it is supported by a cable. So the reaction force that it will provide will be a pull. Okay, so it will be a tension force, and we will label it as T. Okay, so this tension force, okay, that its direction will be applied along the direction of the cable. So since the cable is 60 degrees from the vertical, so this reaction force, which is a tension force, it will also be 60 degrees from the vertical. So this will now be the reaction force that will be provided by the cable. Okay, so now here at point A, so the support here is a hinge support. So for hinge support, okay, we know that there will be two reaction forces, so that will be horizontal and vertical reaction. So we will name our horizontal and vertical reactions here as AH and AV. Now here, we are going to assume, okay, the direction, okay, of AH and AV. But here, we will base our assumption, okay, on the system. Okay, we will analyze this system. So let's say we have here a bar AB, okay, and it is pushed, okay, here this way. It is pushed this way at point E. So if the bar AB is actually pushed, okay, at that point, okay, so what will happen is that it will be pushed. Of course, it will be pushed, right? So and at the top part, okay, of this rod AB, okay, it is pull here, right? So it is being pushed here and it is being pulled here. So the tendency, okay, the tendency of the movement, okay, of this system, if this is being pulled, or if this is being pulled by the tension T, okay, and this is being pushed by force NE, what will happen what will happen is that the rod AB will move like this, right? So it should be resisted, okay, by the support at point A. So it should be resisted. So to resist that, okay, to resist that movement, again, the movement of this rod AB, if it is pulled here and if it is pushed here, it will move like this, right? So it will move like this, right? This bar, it will move like this. So it has to be resisted by the reaction forces here at AH and AV. That's why it should be your AH, it should be directed to the left so that it can resist, okay, its movement, which will be to the right. It will move to the right. If it is pull, if it is pull downward, no, or this way, no, so it will move this way, right? This rod will move this way, so it has to be resisted by AH. And also your AV, okay, so uh since it will be downward, no, so this tension T is actually downward, no, so from here we can actually assume that that your AV, okay, it should be upward, right? Since your tension force here is downward, right? So this AV, it should be upward, okay? So that it can, because if we sum up vertical forces, okay, if we sum up vertical forces, uh, uh, your T, okay, since this is downward, right? So your AV, it should be upward. Okay, just to resist the no, to make the system in equilibrium. Okay, so this will now be the free body diagram. So again, you have to show here the dimensions also. Okay, so this will now be the free body diagram of rod AB. Okay, so this will now be the answers for this problem. So now let's proceed to sample problem number 3. The frame shown is supported in pivots A and B. Each member weighs 50 pounds per feet. Draw an FBD of each member and FBD of the entire structure. Okay, so it is mentioned here that the frame is supported in pivots at A and B. So these are the supports for A and B. So these are pivots. So pivots, okay, so they are also equivalent to hinge or pin supports. Okay, so for this type, okay, of supports, they have actually two reaction forces. So one horizontal and one vertical. So it's just really equivalent, okay, to the reaction forces that hinge or pin supports provides, no? So we are asked here to draw the free body diagram of each member, and here the weight, okay, of each member, it is mentioned that they are 50 pound per feet. Okay, so based on the unit given here, the unit of the weight is pound per feet. Okay, so meaning to say, the weight, okay, are not point loads. Okay, they are not point loads. So these are actually uniformly distributed load, no, for weight, wherein the unit is pound per feet. Okay, so since the unit is pound per feet, we have to multiply this 50 pound per feet, okay, to the length, okay, to the length of the member that we are solving. Okay, to cancel the feet, no, and to solve for the equivalent point load, okay, of this 50 pound per feet intensity, no, of the weight of the members. Okay, and that equivalent point load, it will be applied, no, to the center of gravity, or to the center, okay, of the members, no. So we will start answering this now. Okay, so here we are going to construct the free body diagram, okay, of each member. Okay, so to construct the free body diagram of each member, it is advisable that we start, okay, with the member that has a load. Okay, so that we can, from that load, okay, we can assume, okay, the right direction, or the right assumption of direction of the reaction forces that we are going to draw or show in our free body diagram. So in here, the member here that has a load, okay, is this bar or member CE. Okay, so we will start constructing the free body diagram of member CE. Okay, so we will start here. Okay, so for the FBD of member CE, so again, our first step, we have to um, draw the member CE, assuming that its supports, okay, are removed. So the supports of this bar CE, okay, or member CE, so it is supported by a pin here at point C. Okay, so it is also supported by a pin here at point D, right? And so those will be the support. So we will remove them. Okay, so we will draw the the rad CE. Now, and after that, we are going to draw, okay, or show the applied forces. So here, the applied forces will be the 200-pound force, okay, or 200-pound load. So it will be shown here. So of course, since this is a weight, no, this is also a weight, this 200-pound load, so it should be directed downward. Okay. So also, we also have a weight for each member. So as mentioned in the problem, each member weighs 50 pound per feet. Okay, so we have to multiply that 50 pound per feet, okay, to the length of this member. So the length of this member is actually 8 plus 4. So that will be 12. Okay, so multiplying 50 pound per feet, okay, times 12 feet. So feet will be canceled, and the answer will be 600 pounds. So that will be the equivalent point load, okay, of the weight, okay, of bar CE, and it will be applied here at the center of gravity, or at the center of this member CE, no, which is at this point. Okay, so after that, our step 3, we have to show the reaction forces that are provided by the support. So again, we will start showing or providing the reaction forces, okay, to the support, okay, that we can assume, okay, our the direction, okay, properly, okay, based on the given load, no. So here, the load is 200 pounds. So if this member will be pulled, okay, by this 200-pound force this way, okay, so the tendency is that this member CE, okay, it will be moved, okay, downward, okay, and it will be pulled down, right? It will be pulled down, okay, so the tendency is it will also move, okay, since it will be pulled down, okay, so this member CE, it will move this way, right? So it will move this way since there's a support here, so it will move this way. Okay, since it will be pressed or it will be pulled, okay, downward here. Okay, so this pin at point D, okay, so it should react, okay, so that this member CE, okay, will be at equilibrium. Okay, so the reaction, the horizontal reaction here should be at it should be directed to the left, okay, so that it can resist, okay, the motion of this caused by the 200-pound load. So if this is pressed, okay, downward, this part will actually move, right? It will move to the right, so it has to be resisted by DH, no, so it has to be directed to the left. Okay, so your DV also, since it will be pulled downward, so your DV, it should be upward, right? So your assumption here will be upward. So still, no, these assumptions are not sure yet, no. So these assumptions, okay, will be proved correct, okay, in our solution. So in this case, it's okay if we assumed it wrong, no. But here, this will be our assumption. Okay, so if our horizontal reaction here is directed to the left, okay, so here at pin C, okay, or yeah, pin support at point C, so there will also be two reaction forces here, one horizontal and one vertical. Okay, so this CH, since the DH here is directed to the left, so to keep this member in equilibrium, okay, so it should be directed now to the right. Okay, just to maintain the equilibrium, okay, for this free body diagram. Ayun. So also, this CV, we will assume that it is directed upward, no? So since we have also here a weight W, okay, so if it will press, since this bar CE, no, and the support is here, so this vertical reaction are supposed to be supporting this weight W as well. So it should be upward. No? So again, our assumptions here, they may still be wrong. Okay, so it will now depend, no, in our solution. Okay, so but for this, no, so this will be the free body diagram now of our member CE. Okay, so now we will proceed to the free body diagram of member FD. Okay, so again, our first step, we will remove this member FD from, or we will remove the supports, okay, for member FD. So the supports here is also pin here at point F and pin here at point P. Okay, so we will also show here the applied forces. So in this case, the applied forces will be the weight. So the weight here, okay, so all the members, as mentioned in the problem, are 50 pound per feet. Okay, so the length of this member, okay, so actually it's not here in the dimension, right? We don't know the length, okay, of this member FD, but we can use the given dimensions here, which are 8 and 6, right? So if this is 6 and this is 8, and this will actually be the hypotenuse of the triangle that will be formed, right? So what will happen here is that to solve for the length, okay, of this FD, we will use Pythagorean theorem here. So that will be square root of 8 squared plus 6 squared. So inputting that in our calculator, square root of 8 squared plus 6 squared. So that is actually equal to 10. Okay, so from that, no, we know that bars FD, it is actually 10 feet. No, so multiplying that dimension or that length, no, to our 50 pound per feet here, so feet will be cancelled, and the equivalent point load of the weight of this member is actually 500 pound weight, no. So that weight will be applied at the center of bar CD, so it will be somewhere here, no. So of course it will be downward, and also we already have so for our third step, no, we will show here now the reaction forces, okay, provided by the support. So here at point D, we actually already drawn, no, reaction forces provided by pin support at D. So we will just transfer this reaction forces. Okay, so as we transfer these reaction forces, it will be directed oppositely. Okay, so if our DH here is directed to the left, if we transfer it here in the FBD of member FD, so it will be directed to the right. Okay, and for DV, okay, so if it is directed upward here, if we transfer this in the FBD of member FD, so it should be downward here. So your DV will be downward here. So now, for the support here at point F, okay, so for point F, okay, so this is pin connected also. Okay, so for this, there will be two reactions as well, one horizontal and one vertical. Okay, so we will assume, okay, so since your DH here is directed to the right, so your FH here should be directed to the left, okay, to keep this free body diagram in equilibrium. And also, if your, uh, actually this FB, we will just assume this, no? So we don't know if, but since all the forces kasi, no, all the vertical forces here are downward, okay, so your RFB here should actually be upward, okay, just to maintain the equilibrium of the system. So it should be upward, okay. But then again, these assumptions, okay, are not yet proved right, no, unless we have the solution. But in this case, no, this will be now the free body diagram of member FD. Now, we will now proceed to the free body diagram of the remaining member, which is member AB. And so for member AB, at point A, okay, its support is a pivot, no? So pivots are also equivalent to pins or hinge supports, no? So there will just be horizontal and vertical reaction. And also, okay, so for our step 2, no, we have to show here the applied force. So the applied force will be the weight. Okay, so there will also be weight for member AB. Okay, so its weight will just be 50 pound times its length. So its length is 3 plus 6 plus 3, so that will be 12. So multiplying 50 pound per feet times 12, so feet will be cancelled, and that will be equal to 600 pounds. So that will now be the weight of this bar AB. No? So after that, for our step 3, we have to show here the reaction forces. No? So actually, the support or the pin here at C and F, okay, if we are going to transfer, okay, this reaction forces at point C to the FBD of member AB, and this reaction force at point F here, if we transfer it here, they will actually serve as a applied force or applied load already. Okay, since they are not the support of this bar AB, no, so they will serve as a load or applied load, no. So again, if we transfer CH and CV here at point C, so it will be oppositely directed. So if our CV here is upward, it should be downward here. If our CH here is to the right, so our CH here should be to the left. And also for our F, so it is applied here, no? So it should be applied here. So if FV here is upward, so your FB here should be downward. If our FH here is directed to the left, it should be directed here to the right. Okay, so those will be the applied forces, no, for this member AB. Now we're going to draw now, okay, or show now the reaction forces, okay, provided by the support. So it is supported by a pivot at A and B. So it will just be the same as your pin supports, no? So we will assume that our AH will be directed to the right, okay, and your AV will be downward, no? And for pivot at B, so we will assume that your BH will be directed to the right also, and for BV, we will assume that it is directed upwards. Again, these assumptions, we will just prove them right or wrong, okay, in our solution. So it's okay that we make here a wrong assumption, no? So in this case, no, so this will now be the free body diagram of member AB. Now we will proceed to constructing the free body diagram of the entire structure. So again, in constructing the free body diagram of the entire structure, you have to determine first the main supports. Okay, so in this case, the main supports here, okay, will be the pivot at A and pivot at B, right? So they will be the main supports. Okay, so we have to show that in our free body diagram, and also we have to also show, okay, the load 2,000 pound, the weight of and the weight of each member. Okay, so this will now be, okay, the free body diagram of the entire structure. So we show here the reaction at A, the reaction at B, and the loads and the weights here. So this will now be the free body diagram of this entire structure. Okay, so this will now be our last problem. So this is sample problem number 4. So the homogeneous beam AB weighs 400 pounds. For each support condition shown in the figure, draw the free body diagram of the beam and determine the number of unknowns. No, assume frictionless for supports. Okay, so our given here is an beam AB. No, so this is actually fixed supported here at point A. Okay, and this is supported here at point B by a roller, no? So this is a roller. Okay, so let's start. Okay, so again, we are asked here to find the free body diagram of the beam, and we are asked here to count the number of unknowns. Okay, so for the free body diagram of this bar AB, okay, so since we know, okay, that here at point B, so it is just a roller support, so the reaction force, okay, that will be provided here will just be a normal force, okay, and it will be applied here perpendicular to the surface, okay, where the roller is lying, no? So that will be, we will label that as RB, okay, and it is 90 degrees, okay, from this surface, no? So this will just be vertical since the surface here is horizontal, okay, and also we should apply here also, no, so in our step 2, no, so we have to apply here the applied force or applied load, which is the weight of this beam, no? So this is 400 pound and it is applied here at the center, okay, center of gravity of this beam, no? So it will be somewhere here. Okay, and also at point A, it is fixed supported. So for fixed supports, there will be 3 reactions. Okay, so that will be horizontal reaction, vertical reaction, and moment reaction. So we will name the vertical reaction as AV, we will name the horizontal reaction as AH, and we will name the moment reaction as M sub A. Okay, so the assumption of the moment here, okay, is counterclockwise. Okay, but actually, we can assume that, no, the rotation of this, or the rotation of this reaction moment, okay, depending on the load. So since the load here is 400 pound, it will actually produce a uh, it will actually produce a clockwise rotation, right? It will produce a clockwise rotation. Okay, it will produce a clockwise rotation, okay, about point A for this beam. Okay, so meaning to say this moment at A, it should be the opposite. It should be its rotation should be opposite of the rotation that will be produced by this weight na 400 pound, no? So its moment should be counterclockwise. Okay, so that will now be our assumption, okay, for the rotation of the moment reaction here at point A. So it will be counterclockwise. So this will now be the free body diagram of this beam AB, no? So Also, we are asked you to count the number of unknowns. So here, the number of unknowns will be 1 for RB, 2 AV, 3 AH, and 4 MA. So there will be 4 unknowns for this problem. So this will now be the answers, okay, for this sample problem. So that concludes our discussion for this topic. I hope that you learn and I hope that you attain the learning outcomes for this topic. So happy studying, class. God bless and keep safe.